Hi, this is Dr. S and this is video 6 in my series on reaction rates for Year 12 A-Level Chemistry. In this video we'll look at catalysts and how they can affect the rate of reaction. So you've probably heard of a catalyst before, so let's just make sure we can define what a catalyst is. A catalyst is a substance that speeds up a reaction without actually being used up in the reaction itself. And it does this by offering maybe an alternative pathway, an alternative mechanism, or a surface for a reaction to happen on. Either of those two methods would give a lower activation energy. If you remember activation energy, that is defined by the minimum amount of energy required to start a reaction. Now you'll have seen that on reaction profiles that we've done before. So let's just remind ourselves about reaction profiles. Let's draw a reaction profile for an exothermic reaction. As the progress of reaction continues, this is the enthalpy up here. If it's exothermic, we know that the reactants are going to be higher than the products because that gives us a negative delta H. But we also know that there's going to be an activation energy represented on that diagram by a curve, and the activation energy is then the difference between the reactants line and the top of the curve, which is EA. Now if I then add a catalyst, the catalyst will lower the activation energy, so that will affect the diagram by putting a different activation energy curve on here. So now my activation energy is smaller and it requires less energy to get over this hump and then down to the products. One of my next video will look at how that actually works and how that speeds up a reaction. But now what I want to concentrate on is what are the different types of catalysts and how do they work? Okay, so different types of catalyst can be classed as either homogeneous or heterogeneous. Geneous means state in this case. So homogeneous means same state, and heterogeneous means different state. So what that means is if the catalyst itself is in the same state of matter as all the reagents and the products, then it would be homogeneous. Most common example of that would be something like an acid catalyst, where everything is dissolved in water, everything is aqueous. In a heterogeneous catalysis reaction, the catalyst is in a different state from the reagents. Most common example here is maybe when the reagents are gaseous and the catalyst is a solid. So a good example of that is a catalytic converter in a car. The exhaust fumes of a car have some quite noxious gases in there, like carbon monoxide, nitrogen oxides. A catalytic converter is added to an exhaust, which then processes those gases into less harmful gases, such as nitrogen and carbon dioxide. So what you need to know is then how a heterogeneous catalyst works. In a catalytic converter, we have the exhaust tube, and it goes to a little box, and then that's the output. In that box there is lots of sheets of metal that act as the catalyst. Now the catalysts are generally made of platinum or rhodium or palladium, very expensive metals. So you have to use as little metal as possible but have a big surface area. So that's why they make this sort of honeycomb arrangement. Huge surface area for the gas particles to interact with. So what happens when the gas particles do hit the catalyst is they are what we call adsorbed. So it's a process called adsorption. Now be careful with this, it's adsorption. What that means is if there is a catalyst surface, the particles just attach to the surface. They do not go into the actual structure of the catalyst, just the surface. If they're moved into the structure, that would be called absorption. This is adsorption, just on the surface. While they're attached on the surface, they can now interact with other particles easier, which allows a lower activation energy. So that's the point where there is an actual reaction. Once the particles are reacted, there's no need for them to then be attached to the surface anymore, so they are removed, and that is called desorption. So a three-stage process by which heterogeneous catalysis works. Now let's just stop and think about sustainability of reactions. So what that means is limiting the effect, the negative effect of a chemical reaction on the environment. We all know that energy, in order to use energy, we probably have to heat things up, which then burns fuel, which then creates carbon dioxide. So the lower the temperature of a reaction, the less fuel has to be burned, and the less carbon dioxide is released, and the less that impacts on the planet. So let's think about why companies spend millions of pounds investigating effective catalysts for their reactions. It's partly to make sure that their processes are more sustainable. But obviously from a company point of view, it's also because if you can come up with a catalyst that reduces the activation energy so much that you can use less energy, that means you have to burn less fuel, which means it costs a lot less money. So it's a double win for the company. Okay, in my next video, we will look at exactly why reducing the activation energy increases the rate of reaction using something called a Boltzmann distribution. I'll see you then.